Excellent. Thank you very much. So I want to thank VivaTech for having me out. And you mentioned Trudeau's explanation, but I've made it much, much simpler because we have published a book called Quantum Computing for Babies. And so if you are paying attention during the presentation, and if you have questions that come up on the screen at the end of the presentation, then I have brought some of these books to give to you for asking questions. So please feel free to ask the questions as we go along. So I want to focus the talk around three things. But before we go into those, how many of you are aware of quantum computing? You have some knowledge. How many of you are lying about knowing about quantum computing? Thank you, sir. You get a book by default. They should give this man a book for sure. You know what? I give you this book right now. Come here. That is, I love the honesty. Because I travel all over the world, and usually everybody says they know about it, and they really don't. Well, for those of you who don't know in the audience, who didn't raise your hand, quantum computing is going to change computing more in the next 10 years than it has changed in its entire history. Okay? I am not a physicist. I am not one of the people who hypes quantum computing. I'm very realistic about it, but it is coming, and it is going to make an incredible difference in drug discovery and aerospace, material sciences, all manner of areas. And there is a lot of hype around this area right now. But for those of you who don't know, the basic way that it works is you can imagine that you have a coin. If you take this coin, it has a heads and it has a tails, and if you set it on a flat surface, then it is a one if it's a heads, it's a 0 if it's a tails, okay? So in that two-dimensional plane, it's like that. That's how a bit works. Now take that same coin and you flip it in the air. When it is flipping in the air, is it a 1 or a 0? You tell me, right? It is in a superposition of both of those states. So a qubit, unlike a bit, is like a block sphere. And the way we manipulate these is we spin them on the axis and things, and we can use them to solve very complicated problems, NP, NP+, BPQ problems. These are computationally complex problems, and the way that we solve them is because if you have, say, a salesperson, you want to send them to 14 cities, it's a 10 to the 9th problem. You have a 10 to the 11th computer, 1,600 seconds, you're fine. You add 8 cities from 14 to 22, the same machine will take 1,600 years to solve this problem. So it's not that computers can't solve these problems, it's that as we put in minor inputs, the evaluation time of the problem goes up dramatically, and therefore we need a new type of computer to solve these problems. So, as I said, there is a lot of hype in this space, and so I would like to clear some of that up, and I would like to focus the talk on the 3 things that quantum computing needs to become real. And I would like to encourage all of you to get actively involved with this form of computing, because I think it is a huge market, $1 trillion by somewhere around 2035, according to some of the reports, probably $800 million, somewhere between 2025, 800 billion, sorry, and 2030. So let's start with the first thing. This is a long-term investment, okay? This is a trip to Mars to save the species, not a trip to Vegas for the weekend. You have to be very committed with the capital. You have to be very committed with your intentions with your company. If you are a venture fund and you are 5 years in a 10-year fund and you invest in quantum computing, you are not going to get an exit probably in the next 5 years. Okay, so we need more investment, not just from governments, but from venture, from strategics. And we need patience with that investment because this is completely revolutionary. It's not something that is just going to happen because we put out a press release that says we achieved something, okay? One of the things that gets people excited about this is this graphic. So in 1927, we had the 5th Savoy Conference, where quantum mechanics, Irving, Schrödinger, everybody, Einstein kind of came up with the idea. 55 years later, Feynman and Benioff come up with the idea of using a particle as a bit, okay? The concept of a qubit. So 18 years after that, Los Alamos has 7 qubits. And then another 6 years, MIT has 12. And then in the last 3 years, we've went from 17 to 50 to 72 to 128 to 160 qubits. So it's easy to understand why there's a lot of hype. It's easy to understand why there's a lot of excitement and investment in this space. But you have to temper that with reality. And the reality is that we are not in the stage of AMD versus Intel with quantum computing. We're in the stage of mechanical gates versus vacuum tubes. It is very, very, very early in this space still, even though you see this type of progress. The phones you have in your pocket have 3 billion transistors, okay? 160 qubits. Now, a qubit could be worth 1 million bits or more, but even then, it's not even comparable. So we're in the very early days, and we need to make sure that we keep real about that. And everyone you will hear talk about the quantum supremacy, okay? I think this is a bad way to look at it. There will be quantum advantages, there is no doubt, but the fact is that these machines aren't meant to solve the classical problems you're trying to solve today. So right now, when you hear about quantum supremacy, we're trying to prove whether a quantum computer can do something faster than a classical computer. That's thinking very classically. That's shoving a classical model into this new space. These machines, to me, don't represent a faster way to do the problems we have today. They represent a way to create completely new calculations, to solve completely new problems that we have not even dreamed of. Trying to do classical problems on a quantum computer is the equivalent of when first computers came out for offices and people said they're going to be really good at spreadsheets. And no one thought of the internet, no one thought of games, no one thought of any of these things. And that's kind of what we're doing again. So when will quantum computing get here? So the pessimists say 20 years, the optimists say 3. I don't really care. I think we should be preparing for this today, both in educating, high school students, college students. I think we should be providing tools that are free. We should be doing a lot of work in open source and getting more and more people involved in this process and democratizing it. I'll talk a little bit about that more later. But there is a challenge in quantum computing right now, a threat to this. And that threat is simple. Right now, in venture capital, the size of seed rounds has been going up. At the same time, the number of those rounds has been going down. So in the areas of deep tech, very deep science-based startups, getting funding can sometimes be a challenge. And we need more funding across more startups in this ecosystem to make quantum computing be real. There are problems with fidelity. There are problems with entanglement. There are so many technical problems, and we need a lot of startups and a lot of smart people working on this. The reason that this happens is because there's a difference between value and valuation. These are very, very different words. And so right now, the problem we have is some of the startups are getting valued very high in the valuation, but have very little practical value to an enterprise, to a user, from the standpoint of quantum computing. And this is very dangerous because we could find a quantum winter by accident. And what I mean by that is in 1971, Martin Minsky at MIT said, in 3 to 8 years, we'll have a computer that has the average intelligence of a human being. And it is 2019, we still don't have that, and we face the same potential kind of expectation settings and missing these expectations in quantum if we're not very careful. So what's the second thing quantum computing needs? Well, I believe it's only going to become useful through collaboration. I do not think this is a problem that is solved by a company or an individual or a university. I think this is a problem that is solved by a very mass group of people, all applying their different disciplines to the problems that it faces to both build the computers and then to figure out where the algorithms we need are to run on those computers, and then to figure out what the practical applications of those algorithms are in society. So to that effect, I've been doing a lot of stuff that startups don't normally do. We have partnered with CERN and the IEEE and Stack Overflow and done a bunch of stuff. So if you are a member of the IEEE or are interested, you can see me. We have a standard that we are creating. We're actually in talks to partner with ISO on terms and definitions. I found when I traveled around the world that a qubit, D-Wave is an annealer. It's one type of quantum computing, has 2,000, 4,000 qubits. IBM has 20. They're about to have 56. So people can't tell the difference in those machines. So we have one standard on nomenclature, and then we have one standard on performance benchmarking. Because if you go research quantum computing, every company comes out and brags about how much faster their computer is, and then there's some university professor who writes a blog post who says, I wrote software on my Mac on the plane, it's much faster, right? There's no standard for calculating how valuable these things actually are, and that's incredibly important. But probably the best thing that we've done is taken a different approach. As I said, I'm not a physicist, I'm not a mathematician, I'm a software developer. This is my skill, this is my focus. And so we have been working to tie the hardware together with the process of discovery. And I'll talk about unlikely discovery in a few moments, but unlikely discovery is where all great inventions come from. And all of the solutions we want these quantum computers to bring are going to come through unlikely discovery, and they're going to come through collaboration. So if you're a developer, how many people are developers? Okay, you familiar with Stack Overflow? You can go to the site we built with them, quantumcomputing.stackexchange.com. Last March, I was told we would never have more than 50 people in this community. And today, we have 5,370 people. And there are physicists and software developers and mathematicians, and they're all collaborating, working together to provide answers to questions, whether you're building software or building a computer or trying to learn about an algorithm. Is a completely free resource. It's a great resource we're very proud of. And then I've been focusing my time on building some tools, because you can't take a software developer and make them a quantum computing software developer overnight. It is very hard. In the early days of computing, you had to be an electrical engineer to program a computer because you had to understand the flow of electricity between the gates. In the early days of quantum computing, you have to be a physicist or have some very deep physics knowledge to take advantage of these machines. But it won't always be this way. In the future, all software developers will use them. I don't see these as quantum computers. People talk about them like they're going to replace other computers. Think of them like a GPU or a TPU. Think of them as a coprocessor. So you'll write a classical program, and then you'll have some very complicated math. You'll send it to the quantum computer. You'll get a returned, and then you'll continue with your classical programming. This is how these things are going to end up working, regardless of what hype or PR you've seen. This is just how software works, right? So the other thing I've been trying to do is sharing knowledge. So not just through the Stack Overflow community, but trying to find resources where you can start, even if you don't know how to do quantum computing, to start grasping the process. And to that, I'd like to invite you all to quantumcomputing.com, which is the first thing I've released. It is a free website. It ties together multiple platforms. It is, as we say, the power of quantum all in one place, accessible to everyone. And it ties together IBM's Qiskit and Microsoft Q#, Forest Rigetti, Cirque from Google, and also the D-Wave Leap. We are a very small team. That's all we have been able to build in 1 year. But we are adding more platforms all the time. So we will have Fujitsu, Hitachi, Honeywell, Alibaba, any platforms that want to come on, Atos, anything that wants to come on to the platform. It is completely configured to be agnostic of the programming language and agnostic of the hardware. It is built for you to start using quantum computing. And again, it is free. So why? Because if you look at this diagram, to me, the industry right now is focused on the technical problems, on the physics problems, on the hardware. Not enough people are focused on the human problem of that side. How is a geneticist going to find some amazing new discovery trying to learn physics to program this computer? How is somebody in finance going to do the same thing? We need to be focused on the discovery process and the questions, on the problems we're trying to solve, and on the approach we're using to solve those problems. This is incredibly vital. And so back to that unlikely discovery. So if you live in America, many people think the Wright brothers invented flight, right? But the Wright brothers did not invent flight. They were not the first one to fly. Da Vinci was trying to fly, hundreds of people all around the world. The Wright brothers invented a 3-control axis, which made it where you could have a plane and you could not crash, right? So this is a great contribution, but they did not invent flight. And much like that, these solutions that we have for quantum computing are not going to come from 2 guys in a garage in Silicon Valley, okay? But I have 10 guys and 4 ladies in a really big garage in Austin. So, problem solved. But I put this up here. You can take photos of it. Go Quantum at STRANGEWORKS. There's a phone number. There's an address. People from all over the world have been coming to visit our offices, and we invite everyone to come. If you know people in the States that want to collaborate, if you want to collaborate, the idea here is to create community around quantum computing to solve some of the biggest problems facing us as a species. Okay, so our office doors are open. You're welcome to join us at any time. So the third thing that quantum computing needs, it needs to be crazy and creative, but it also needs to be patient. These are not things that are going to be solved immediately. They're not things that are going to be solved in the next year or 2. This will be a 10, 20, 30, 40, 50-year process before you see things normalized. It is extremely important to realize that we will get advantages in the near-term future, but just like computers, there will be new discoveries, new things that are developed, and I believe that once we get to about 400 qubits, that we'll start solving some of the problems with quantum computers, and maybe that path will be accelerated. But still, this is a long-term thing. It is not something where you're going to start a startup and sell it in a year. It's not something where you're going to be using these things in mass production in the next year or two. It's going to take some time, and there's nothing wrong with that. I'm incredibly passionate about these machines and what they do. But right now, we don't have quantum computers. We have really, really good lab equipment that's extremely valuable in exploring the quantum landscape. But I would not quite call them computers just yet. So, why are they valuable? Again, when you were in the US, in the early days of the United States, it would take 6 months to cross the United States. Then trains came along and it took a week, okay? But no matter how good the trains were, eventually you meet an ocean. And so when you think of the role of quantum computing in the larger ecosystem of computing, don't think of it as replacing it, think of it as augmenting it. Quantum computing, right, is to classical computing as planes are to trains. Different mode of transport, different functionality, and they work together. Sometimes you take a train to get to the plane. I just did that from Oslo. So these things are going to be paired, they're going to be collaborative, and they're going to make a dramatic impact. On what? Revolutionizing our science, curing diseases, addressing climate change, something very personally important to me. We'll be announcing a project around climate change later this year. And then basically protecting humanity, right? Solving all of these critical problems that we know that we can do, but we don't have the computational power to achieve. These are all the things I hope will come out of quantum computing. So we owe it to humanity, and we owe it to do it responsibly, and we owe it to do it together. Now, I saved little over 5 minutes, because I can ramble, for questions to give away the books. Somebody has the books, if they could show themselves somewhere. I don't know who is it. There they are. You have the books. Do we have a microphone for the audience for the questions? No, we don't. So you shout really loud. Okay, it's fine. You have a mic? Oh, sorry. You put them on the screen. I forgot. Sorry. I've done 3 conferences this week. I forgot. We had the fancy screen. So let's see. All right, Laura, where are you? Okay, did you ask the how worried are you about people hacking question? Okay, the question is, how worried are you about people, hackers collecting classically encrypted data today to break into it when quantum computing is ready? A little bit, but I think the encryption problem is way overstated. I think it is fear and uncertainty and doubt and fear-mongering to get funding from governments, to get funding from certain agencies and things around quantum computing. Think about how security works. Threat and remediation are in an ever-entwined dance. You build a wall, I build a way to break it down, you build a bigger wall. This has been the history of security. So let's say that I have a quantum computing, and let's say it's 4,600 topological qubits, which is what Microsoft thinks you would need to break a quantum encrypted key. And let's say I break the key. I run that process, I break your key, Laura. I don't break everyone's key. I have to repeat that process for everybody. So if that is the situation, would you not make that key longer? Then I would need 10,000 qubits, right? This is how it will work. I don't worry about that, but I do worry about data that's already been encrypted, because there are national secrets for some of the countries like France and the US and Germany, Great Britain, where there are other countries who would love to find old data like that. I think that there are plenty of ways that you can address that problem, so I don't see it as being some earth-shattering problem. It's certainly not a reason to fear quantum computing. I don't think anyone should be fearing it. So let's see. There's another, Laura, you asked more than one question? Really? Okay, give somebody else a chance to get a book, Laura, please. So, what should a software company do now to be ready to develop quantum computing software? This is Laurent. Where are you? Right there? Okay, we'll send you a book. So this is a great question. There are, you can sign up at quantumcomputing.com and you can, start playing with it. You have to start getting the developers to learn more discrete math, more physics. if you want to start now early, or you have to augment your team by hiring a physicist or someone who's knowledgeable. We have hired 2 already. We plan on hiring 4 more this year and getting them work together. But it's really a matter right now of signing up for whether it be IBM or Rigetti or Microsoft or through a system like ours to get access to the machines to start playing around with experiments. Most of these companies, including mine, offer an experiment library. So for example, if you want to learn quantum teleportation, they explain the protocol and then they explain the software code and then they give you an opportunity to run it. A lot of them use Jupyter notebooks. Which is not something software developers love, but physicists and other people do. So maybe getting some access to some of those is probably pretty valuable. All right. I think quantum computing is... So that's another Laura question. Laura, how many questions did you ask? Just, okay. So Anonymous, really? You don't want a book? Says, how long can we expect to see the arrival of high-level quantum programming languages? Every company is already working on that. And if Anonymous, if you want to raise your hand, you can get a book, but otherwise we'll skip over you. But everybody is working on that. How long before it's real? Abstracting quantum computing for a developer doesn't necessarily help in this case because I can abstract teleportation, but the moment the developer has to debug or whatever, you instantly have to understand what's going on with the physics. So there's kind of not a really great way around that right now. How do you feel, Adam? Where's Adam? How do you feel with the quantum internet? Are the protocols going to be challenging? There's Adam right there. Yes, I'm very excited about it. But the quantum internet doesn't come without problems, and some of the challenging problems will be in physics. There was recently a paper published that said if 3 actors set off the right pulse at the right time, then the entire quantum internet would go down and be unrecoverable because of the physics, right? So the protocols will be, I think, very simple. I think we will abstract those pretty easily, but the maintenance of the network, physically, as far as the physics are concerned, I think that could be very challenging. All right, so we have 1, 2, 3, we have 2 more. Benoit? All right, give this gentleman a book. I'm going to say, I will talk to you this after, but his question was, Hurley, please give me the elevator pitch to convince my boss that quantum computing has anything to do with the luxury industry at all. Right? So here's my, so here's my pitch. I have the Chanel Pharrell shoes, and I know quantum computing. I will talk to your boss for you. No, look, analytics are something, I mean, depending on the size, you want mass scales, but there are plenty of things that eventually you'll be able to use. Do you need quantum computing to do them? That's the question. This is not meant for everything, right? But there will be all manners of opportunities. For luxury industry, my assumption would be that as you look at things that are mined around the world and how you want to use blockchain to track where the sources come from and start finding new things, that you would be very interested in material science so that a luxury brand could have a material that was made ethically, right, that they used in their products. So that would be something I would think about. All right, and then for our last question. So many questions. Yes, oops, the questions disappeared. Can I get the questions back for 1 second? Ah, there we go. Another anonymous. Marco, where's Marco? Marco's right there. Do you think cloud and quantum are/will be related? Yes, they're completely intertwined. Not just in what we were asked about earlier about the quantum internet, but in that right now for the visible future, building actual quantum computers, because of all of the interference from everything in the environment, requires shielding, encasing, the cryogenics to get them cool. So most likely, the only way you'll access them is over the cloud for the foreseeable future. Now, there are alternative platforms, like Fujitsu's quantum-inspired platforms, Hitachi's quantum-inspired, that are CMOS architecture, that those will be sold. But for actual machines that use the physics, yes, it's probably over the cloud. And that is my time. Thank you very much, everyone. Have a wonderful time at VivaTech.